Right now, there is a planet 25 million miles from Earth that looks like it should be our closest twin. It is nearly the same size, nearly the same mass, orbiting the same sun, just one lane closer. For centuries, scientists assumed it might harbour oceans, forests, maybe even life. They were catastrophically wrong. Beneath a blinding white veil of clouds lies a surface hot enough to melt lead, crushed under pressure, equivalent to being half a mile beneath the ocean, bathed in an atmosphere of carbon dioxide so thick it behaves almost like a liquid. The most advanced lander ever sent there survived for 2 hours and 7 minutes before the planet destroyed it. Venus is not a dead world. It is an active planetary nightmare, and it is right next door. If you enjoy journeys that completely change how you think about our place in the solar system, take a moment to hit that like button and subscribe. It genuinely helps this channel keep making these deep dives into the universe. Now, settle in and get yourself comfortable. Let's begin. For most of human history, Venus was the most promising world in the solar system. Not Mars, not Jupiter's moons, not any of the exotic bodies we have since catalogued with robotic spacecraft and orbital telescopes. Venus, the second planet from the Sun, the closest planet to Earth. A world so similar in size, mass, and basic composition that generations of scientists considered it our planetary sibling. Some went further and called it our twin. That word appeared in textbooks, lectures, mission proposals, and popular science articles for the better part of a century. It was not careless, it was earned. The physical resemblance between Venus and Earth is so striking that if you saw them side by side, without any atmospheric data, without any surface measurements, without any of the information we now take for granted, you would struggle to explain why one should be dramatically different from the other. Start with the basics. Venus has a diameter of approximately 12,104 kilometers. Earth's diameter measures approximately 12,742 kilometers. That difference, roughly 638 kilometers, means Venus is about 95% the width of Earth. To put that in perspective, the gap between the two planets' diameters is smaller than the width of the continental United States, measured from the coast of South Carolina to the coast of Southern California. If you placed 2 billiard balls next to each other on a table, and one was 5% smaller than the other, you would need a ruler to tell which was which. That is the physical relationship between Venus and Earth. Nearly the same sphere, nearly the same volume, nearly the same object. Mass follows a similar pattern. Venus weighs in at approximately 81% of Earth's mass. Its surface gravity is roughly 90% of what you feel standing on the ground right now. If you weigh 180 pounds on Earth, you would weigh about 163 pounds on Venus. You would not float. You would not feel dramatically lighter. You would notice the difference the way you might notice a slightly thinner pair of shoes. The internal structure reinforces the comparison. Both planets have iron cores, silicate mantles, and rocky crusts. Both formed from the same region of the protoplanetary disk approximately 4.5 billion years ago, built from the same raw materials, shaped by the same gravitational processes, baked in the same young sun's radiation. In terms of raw planetary architecture, Venus is the closest thing to a copy of Earth that exists anywhere in the known solar system. And then there is proximity. Venus is our nearest planetary neighbour. At its closest approach, it passes within roughly 38 million kilometers of Earth. No other planet comes closer. Mars at its nearest still sits more than 55 million kilometers away. Venus occupies the inner lane of the solar system's habitable neighbourhood, sitting roughly 108 million kilometers from the Sun compared to Earth's 150 million. The gap between the two orbits is not vast by solar system standards. It is smaller than the distance separating Earth from Mars when the two are on the same side of their orbits. Venus is right there, close enough that it becomes the brightest natural object in our sky after the Sun and Moon. Close enough that ancient civilizations independently noticed it, tracked it, named it, and in many cases associated it with beauty, love, or divine favor. The Romans named it after the goddess of love. The Babylonians called it Ishtar. The Maya tracked its cycles with obsessive precision. building entire calendar systems around its appearance as the morning star and evening star. For thousands of years, Venus was not a source of fear or dread. It was a jewel, the most beautiful point of light in the sky. That beauty was part of the trap. Venus is shrouded in a permanent, unbroken layer of bright white clouds that reflects roughly 75% of the sunlight striking it. This extreme reflectivity, called albedo, is what makes Venus so brilliant to the naked eye. But it also means that no Earth-based optical telescope, no matter how powerful, can see the surface. When Galileo pointed his telescope at Venus in 1610, he saw phases, proof that Venus orbited the Sun rather than the Earth, but he could not see terrain. He could not see color variations. He could not see landforms. He saw a featureless white disk that changed shape as the planet moved through its orbit. Every astronomer who followed him for the next 3.5 centuries saw essentially the same thing, a beautiful, luminous, impenetrable mask. This visual silence created a vacuum, and human imagination rushed to fill it. Because Venus was so close, so similar in size, and hidden behind clouds that could easily be interpreted as a thick, water-laden atmosphere, scientists and writers alike concluded that Venus was probably warm, wet, and possibly alive. The logic felt airtight at the time. Clouds on Earth form from water vapor. Venus has thick clouds. Therefore, Venus must have abundant water. A planet with abundant water closer to the Sun than Earth would be warmer. A warmer, wetter world would logically be tropical. The conclusion was almost irresistible. Venus became a jungle planet in the popular imagination, and remarkably, in serious scientific speculation as well. In the 1920s and 1930s, prominent astronomers including Svante Arrhenius proposed that Venus might resemble a younger Earth, perhaps covered in swamps, ferns, and primitive life. Science fiction writers adopted this vision enthusiastically. Ray Bradbury set stories on a rain-drenched Venus. C.S. Lewis imagined floating islands on a Venusian ocean in his novel Piralandra. Edgar Rice Burroughs populated Venus with entire civilizations. The imagery was consistent and vivid. Venus was Earth's lush, steamy, slightly younger sister, a world of warmth and water hiding behind its veil of clouds. Even as late as the 1950s, respectable planetary scientists maintained that Venus might have surface oceans. The reasoning had evolved slightly. Spectroscopic analysis of Venus's atmosphere had revealed that the clouds were not straightforwardly water-based. There were anomalies. The detected carbon dioxide concentration was surprisingly high, but the measurements were limited by the technology of the era, and the prevailing assumption remained that the surface conditions would be, at worst, hot but potentially survivable. The phrase Earth's twin persisted because the structural similarities were real and the atmospheric data was too coarse to definitively rule out moderate surface conditions. Then, everything changed. The first crack came not from theory but from observation. In 1956, astronomers at the Naval Research Laboratory in Washington pointed a radio telescope at Venus and detected something alarming. Radio waves, unlike visible light, can penetrate clouds. When they measured the microwave emissions from Venus, they were measuring thermal radiation from the planet's surface and lower atmosphere. The signal indicated temperatures far above anything the tropical Venus model could accommodate. The results, formally published in 1958, suggested surface temperatures in the range of 300 to 400 degrees Celsius. The numbers were shocking. Some researchers initially suspected the readings were somehow contaminated or misinterpreted. Perhaps the radio signal originated from the upper atmosphere, not the surface. Perhaps electrical discharges in the clouds were producing anomalous emissions. But as measurements from multiple observatories accumulated through the late 1950s and early 1960s, the picture hardened. Venus was blisteringly hot, not warm, not tropical, furnace hot. Around 1960, University of Chicago graduate student Carl Sagan, still early in his career, published work that offered a physical explanation. The carbon dioxide detected spectroscopically, Sagan argued, could be trapping enormous amounts of heat near the surface through a runaway greenhouse effect. If the greenhouse mechanism was strong enough, Venus would not be tropical at all. It would be an oven. The hypothesis fit the radio data precisely. but it still needed direct confirmation from a spacecraft. The first direct flyby confirmed the worst. In December 1962, NASA's Mariner 2 spacecraft passed within 35,000 kilometers of Venus, carrying a microwave radiometer capable of probing below the cloud layer. Mariner 2's data confirmed that the surface temperature was at least 425 degrees Celsius. The probe also found no detectable magnetic field and no evidence of a break in the cloud cover. Venus was not an inviting world hidden behind a curtain of mist. It was a superheated, magnetically naked planet wrapped in an opaque chemical shroud. Mariner 2 did not orbit or land. It flew past in minutes and continued into solar orbit, but those minutes ended the era of the tropical Venus forever. The twin was not a twin. Something had gone terribly, irreversibly wrong. The Soviet Union attempted what no one else dared. Beginning in the mid-1960s, the Soviet space program launched a series of missions toward Venus that constitute one of the most ambitious, punishing, and instructive engineering campaigns in the history of space exploration. The program was called Venera, and its early missions were a catalogue of destruction. Venera 3 reached Venus in March 1966, becoming the first human-made object to impact another planet's surface. But it failed during descent and transmitted no data. Venera 4 entered the atmosphere in October 1967. It was designed to withstand conditions that scientists considered extreme at the time, temperatures up to roughly 320 degrees Celsius and pressures up to approximately 25 atmospheres. The probe survived to an altitude of roughly 25 kilometers above the surface before the atmosphere crushed it. Crushed it, not overheated it, not corroded it. The pressure exceeded the structural tolerance of the spacecraft before it ever reached the ground. Scientists revised their models upward, astonished. Venus was not merely hot. Its atmosphere was heavy beyond anything they had anticipated. Venera 5 and Venera 6, launched in January 1969, were reinforced. They survived deeper into the atmosphere, reaching altitudes of roughly 18 to 20 kilometers. Then they, too, were destroyed by pressure. Neither reached the surface. Each probe transmitted increasingly alarming data during its descent. The temperature rose steadily and relentlessly. The pressure climbed in a curve that seemed to accelerate as the probes fell lower. The atmosphere was thickening faster than linear models had predicted, because carbon dioxide at these temperatures and pressures was not behaving like a gas in any familiar sense. It was approaching conditions that physicists associate with supercritical fluids, a state of matter where the distinction between liquid and gas effectively vanishes. Venera 7 finally reached the surface in December 1970. It was the first spacecraft in history to land on another planet and transmit data back to Earth. The signal was faint. The probe had landed at an awkward angle, possibly tipped over by wind or terrain, and its antenna was not properly oriented. But for 23 minutes, it sent back readings. The surface temperature was approximately 475 degrees Celsius. The pressure was approximately 90 atmospheres, 90 times the pressure you feel at sea level on Earth, equivalent to being submerged beneath roughly 900 meters of ocean water. The atmosphere was not merely thick, it was crushing. Any unprotected human standing on the surface of Venus would be simultaneously incinerated, suffocated, dissolved by trace sulfuric acid vapor, and compressed with a force equivalent to having a small car balanced on every square inch of their body. And the probe that confirmed this survived less than half an hour. Venera 8 followed in July 1972, transmitting for approximately 50 minutes. It confirmed the temperature and pressure readings and added a startling detail. There was still measurable light at the surface. Despite the enormously thick cloud layers, a faint diffuse illumination penetrated to ground level. The surface of Venus was not pitch dark. It was dim, like a deeply overcast day on Earth, with a reddish-orange glow filtered through hundreds of kilometers of dense, chemical-laden atmosphere. This detail made the surface somehow more vivid and more unsettling. You could see on Venus. You could look around. You would just not survive the experience long enough to process what you were looking at. The later Venera missions would go on to return the only photographs ever taken from the surface of another planet beyond Earth and Mars. Venera 9 and 10, arriving in October 1975, sent back the first black and white panoramic images. They showed a landscape of flat, angular rocks, some fractured, some layered, scattered across what appeared to be a basaltic plain. No sand dunes, no smooth erosion features, no evidence of liquid water at any point in the recent geological past. The surface looked ancient, volcanic, and harsh. Venera 13, which landed in March 1982, achieved the most remarkable success. It transmitted the first colour photographs from the surface of Venus. The images showed a rocky terrain bathed in a deep orange glow. The light filtered through the immense carbon dioxide atmosphere and sulfuric acid cloud layers above. The rocks were flat and plate-like, resembling cooled lava flows. The sky was not blue. It was not white. It was a thick, oppressive amber haze. The spacecraft survived for 2 hours and 7 minutes. It had been designed to last 32 minutes. Engineers had built it as the most heavily armoured planetary lander ever constructed, fortified against conditions that would destroy any conventional spacecraft within minutes of arrival. Even with all of that engineering, the planet killed it in just over 2 hours. The heat soaked through the insulation. The electronics failed. The signal went silent. Venera 13 holds the record for the longest survival time of any spacecraft on Venus's surface. No human-made object has done better in the more than 4 decades since. Think about that for a moment. In the 1960s, scientists designed probes that they believed were conservatively overbuilt for the expected conditions. Venus destroyed them before they reached the ground. In the 1970s, they redesigned the probes based on the new data, armouring them against pressures and temperatures that were already extreme. Venus destroyed those in under an hour. In the 1980s, they threw everything they had at the problem, designing landers that pushed the absolute limits of materials, science, and thermal engineering. Venus destroyed the best of them in 2 hours and 7 minutes. No subsequent mission has even attempted to land on the surface. The planet has not been touched by a human-made object since 1985, when Vega 2's lander reached the surface during a combined Venus-Halley's Comet mission. It survived for approximately 56 minutes. Every machine we have ever sent to the surface of Venus has been destroyed. Every single one. Some lasted minutes. The best lasted just over 2 hours. The planet does not merely resist exploration, it annihilates the tools we send. And those tools were not fragile. They were among the most robust machines ever engineered for planetary science. They were simply not robust enough. Nothing we have built has been. The shift in scientific understanding was total. Within roughly 25 years, Venus went from being the most hopeful candidate for extraterrestrial life in the solar system to being the most hostile solid surface ever directly measured by human instruments. The tropical paradise was a furnace. The potential ocean was a superheated chemical wasteland. The twin was a nightmare, and the cloud-covered face that had looked so serene and inviting through centuries of telescopes was not hiding a garden. It was hiding a catastrophe. But here is the detail that transforms Venus from merely dangerous into something genuinely terrifying. If Venus were a small, distant, structurally alien world, its hostility would feel academic, a curiosity for specialists, a data point in a catalogue of extreme environments. There are plenty of hostile places in the solar system. Mercury's sun-facing surface reaches over 400 degrees Celsius, but Mercury is a tiny airless rock with no atmosphere to speak of. Jupiter's radiation belts would kill an unshielded human in minutes, but Jupiter is a gas giant with no surface to stand on. The moons of the outer solar system are frozen, irradiated, and remote. These places are hostile, but they are hostile in ways that feel appropriately alien. They are different enough from Earth that their extremity is unsurprising. Of course, a gas giant is dangerous. Of course, an airless rock baking in direct sunlight is uninhabitable. The hostility matches the alienness. Venus breaks that pattern. Venus is not alien. It is familiar, almost exactly the same size, almost exactly the same mass, almost exactly the same density, made of almost exactly the same materials, formed in almost exactly the same part of the solar system. It is the planet in our neighbourhood that should, by every structural measure, most closely resemble our own. And it is the one that became the most hostile. That is the dissonance. That is the source of something deeper than scientific fascination. That is the thing that makes Venus feel less like a neighbouring planet and more like a warning written in rock and fire. The question that drives the rest of this story is not what Venus is. We know what Venus is. We have temperature readings, pressure measurements, atmospheric composition data, radar maps, and surface photographs. The question is how. How did a world this similar to Earth, this close to Earth, this structurally familiar, become one of the most comprehensively lethal environments ever documented? What went wrong? When did it happen? Could it happen again? The answer begins with the atmosphere, and the atmosphere of Venus is not merely thick or hot or toxic. It is all of those things simultaneously, operating at scales that no other planet in the solar system can match. What comes next is the full accounting of what that atmosphere actually does, layer by layer, compound by compound, from the cloud tops to the scorched and lightless surface below. The anatomy of a planetary nightmare. Most hostile environments in the solar system can be summarized in a single sentence. Mercury is an airless rock scorched by unfiltered sunlight. Mars is a frozen desert with almost no atmosphere. Titan is a methane-soaked ice world orbiting 1 billion kilometers from the Sun. Each of these places is deadly, but each is deadly in one dominant way. You can describe the primary threat in a few words and the listener immediately grasps why it would kill you. Venus does not work like that. Venus cannot be summarized in a single sentence because the danger is not one thing. It is everything, operating simultaneously, at scales that individually would each qualify as extreme and collectively produce something without precedent on any measured world. To understand why Venus is the most terrifying planet we know, you cannot point to a single number. You have to walk through the entire system, layer by layer, from the cloud tops down to the surface, and watch how each layer adds another dimension of hostility on top of the one before it. But before descending through the atmosphere, it is worth understanding something strange about the planet itself. Venus rotates backward. Every other rocky planet in the inner solar system, Mercury, Earth, Mars, rotates from west to east, counterclockwise when viewed from above the North Pole. Venus rotates from east to west. If you could stand on its surface and somehow survive long enough to observe the sky, you would see the sun rise in the west and set in the east. The reversal is called retrograde rotation, and no one is entirely certain why Venus has it. The leading hypotheses involve either a catastrophic impact early in the planet's history that flipped its rotational axis, or long-term gravitational interactions between Venus's thick atmosphere and the Sun that gradually slowed and reversed the spin over billions of years. What is certain is the consequence. Venus rotates extraordinarily slowly. A single sidereal day, one full rotation on its axis, takes approximately 243 Earth days. That is longer than a Venusian year, which lasts approximately 225 Earth days. Venus takes longer to spin once on its axis than it does to orbit the Sun. The resulting solar day, the time between one sunrise and the next, as observed from the surface, lasts approximately 117 Earth days, nearly 4 Earth months of continuous daylight, followed by nearly 4 Earth months of darkness. On any world with a thin atmosphere, this would create enormous temperature swings between the day and night hemispheres. On Venus, it barely matters. The atmosphere is so massive, so thermally dense, that it stores and circulates heat with an efficiency that renders the day-night cycle almost irrelevant at the surface. The temperature at midnight on Venus is virtually indistinguishable from the temperature at noon. The planet's own bizarre rotation, which should produce extreme thermal contrasts, is overridden completely by the atmosphere that encases it. Even the way Venus turns on its axis has been neutralized by the hostility of its sky. Begin at the top of that sky. Venus is wrapped in a global cloud layer that stretches from roughly 48 kilometers above the surface to approximately 70 kilometers altitude. These are not water clouds. They are composed primarily of sulfuric acid droplets mixed with trace amounts of water. Concentrated sulfuric acid, the same substance that in industrial applications dissolves metals, chars organic material on contact, and must be stored in specially lined containers because it will eat through most common materials over time. On Venus, this substance forms the dominant cloud chemistry of an entire planet. The droplets range from submicron particles, far smaller than anything visible to the naked eye, up to a few microns in diameter, roughly one order of magnitude smaller than typical water cloud droplets on Earth. These clouds are dense enough to be completely opaque at visible wavelengths. No sunlight in the normal sense reaches the surface of Venus. What does penetrate is a diffuse, deeply filtered residual glow, predominantly in the orange and red end of the spectrum, that gives the lower atmosphere and surface its characteristic dim, amber illumination. Standing beneath the clouds of Venus would be like standing inside a vast enclosed space lit by a fading ember, except the space extends in every direction to the horizon, and the ceiling is a permanent, featureless chemical haze that has not broken in millions of years. The sulfuric acid clouds do something else that sounds almost poetic until you think about the chemistry involved. It rains on Venus. Sulfuric acid precipitates from the cloud layer in droplets, falling downward through the atmosphere exactly the way rain falls on Earth. But this rain never reaches the ground. As the droplets descend below the cloud base into the increasingly hot lower atmosphere, the rising temperature evaporates them. Somewhere around 30 kilometers altitude, the sulfuric acid rain has been completely vaporized, converted back into gaseous sulfur compounds and trace water vapor, which are then lofted back up into the cloud layer by atmospheric convection, where they recondense into fresh droplets and begin the cycle again. Scientists call this phenomenon virga, rain that evaporates before reaching the surface. On Earth, virga is an occasional meteorological curiosity, visible as faint streaks beneath distant clouds in dry desert climates. On Venus, it is a permanent, planet-wide phenomenon, an entire world where acid rain falls continuously from the sky and never touches the ground, not because the planet is too dry, but because the atmosphere below the clouds is too hot for any liquid to survive the descent. The surface of Venus has not been touched by rain of any kind in billions of years. It exists beneath a sky that perpetually rains acid and perpetually incinerates that rain before it arrives. These clouds are not passive. They participate in one of the most mysterious atmospheric phenomena in planetary science, a process called superrotation. The upper atmosphere of Venus circles the entire planet in approximately 4 Earth days. Venus itself rotates extraordinarily slowly, and it rotates backward relative to most other planets, from east to west rather than west to east. This means the upper atmosphere winds are moving roughly 60 times faster than the planet's own surface rotation. On Earth, atmospheric winds are driven primarily by solar heating and the Coriolis effect generated by our planet's relatively rapid spin. Venus spins so slowly that this mechanism should produce negligible wind. Yet the upper atmosphere screams around the planet at speeds reaching approximately 360 kilometers per hour. The energy source and maintenance mechanism for this superrotation remain subjects of active scientific investigation. Multiple hypotheses exist involving thermal tides, planetary scale wave dynamics, and momentum transfer between atmospheric layers, but no single model has fully reproduced the observed wind speeds from first principles. The planet's own atmosphere is doing something that our physics cannot yet completely explain. Below the cloud deck, things get worse. Between roughly 48 kilometers and the surface, the atmosphere is clear but extraordinarily dense. It is composed of approximately 96.5% carbon dioxide, with most of the remainder being molecular nitrogen, around 3.5%, plus trace quantities of sulfur dioxide, water vapor measured in parts per million, carbon monoxide, and other minor constituents. This composition alone is lethal to any oxygen-breathing organism. But the lethality of the chemical makeup is almost beside the point, because the physical conditions of the atmosphere are so extreme that biology becomes irrelevant long before chemistry does. As you descend through the clear lower atmosphere, the temperature rises and the pressure increases with a relentlessness that is difficult to overstate. At the cloud base, roughly 48 kilometers up, conditions are already punishing. Temperature at that altitude sits in the range of approximately 100 to 150 degrees Celsius, well above the boiling point of water. Pressure is several times Earth's sea level atmosphere. But you are still 48 kilometers above the ground. The descent has barely begun. At 30 kilometers altitude, the temperature has climbed past 300 degrees Celsius. The pressure has risen to approximately 40 to 50 times Earth's surface pressure. Lead begins to soften at around 327 degrees Celsius. You are still above the surface, and the atmosphere is already approaching conditions that would melt common metals. The density of the gas around you is increasing with every kilometer of descent. Carbon dioxide at these temperatures and pressures is no longer behaving the way most people imagine a gas behaves. It is thickening, resisting motion, beginning to exhibit properties intermediate between a gas and a liquid. At approximately 15 to 20 kilometers altitude, you cross a threshold that physicists call the critical point for carbon dioxide. The critical temperature for carbon dioxide is approximately 31 degrees Celsius, and its critical pressure is approximately 73 atmospheres. On Venus, at altitudes below roughly 15 to 20 kilometers, the atmospheric temperature and pressure both exceed these critical values. The carbon dioxide becomes a supercritical fluid. This is a state of matter that does not exist in everyday human experience. A supercritical fluid has the density of a liquid, but fills space like a gas. It has no defined surface, no meniscus, no distinct boundary between liquid and gas phases. It flows, diffuses, and dissolves substances with properties intermediate between the two familiar states. Walking through the deepest atmosphere of Venus would not feel like walking through air. It would feel like wading through an invisible, searing hot medium that resists your movement, presses against every surface of your body, and fills every crevice and gap with a density approaching that of water. Except it is 465 degrees Celsius and exerting 92 times the pressure of Earth's atmosphere at sea level. The surface itself sits at the bottom of this column of superheated, supercritical carbon dioxide. The temperature at the surface averages approximately 465 degrees Celsius, roughly 870 degrees Fahrenheit. This temperature is remarkably uniform across the entire planet. Dayside, nightside, equator, poles, highlands, lowlands, the variation is only a few tens of degrees at most. This uniformity is itself a product of the atmosphere's immense thermal mass. The sheer weight and density of the carbon dioxide envelope stores and redistributes heat so efficiently that the surface never significantly cools, not during the long Venusian night, which lasts approximately 117 Earth days, and not at the poles where sunlight arrives at oblique angles. There is no seasonal variation. There is no diurnal cycle of warming and cooling that any human would recognize. The temperature simply persists, day after day, century after century, stable enough to soften lead continuously at every point on the surface. The pressure at the surface is approximately 92 bar. 1 bar is roughly equivalent to the atmospheric pressure at sea level on Earth. The weight of the entire column of air above you pressing down on every square centimeter of your body. On Venus, that weight is 92 times greater. The closest equivalent on Earth would be the pressure you would experience approximately 900 meters beneath the surface of the ocean. Imagine being submerged at that depth, nearly a full kilometer down, in an ocean not of water but of dense, blisteringly hot carbon dioxide laced with sulfuric acid residue and sulfur compounds. That is the closest terrestrial analogue to standing on the surface of Venus, and even that comparison understates the alienness, because the ocean at 900 meters depth is cold and dark, while Venus is simultaneously at crushing pressure and at temperatures that would ignite paper and melt tin. Surface winds on Venus are slow by Earth standards, typically measuring only a few kilometers per hour. On Earth, a wind of 3 or 4 kilometers per hour would barely rustle leaves. But wind force depends on the density of the medium, not just its speed. The atmosphere at Venus's surface is so dense, roughly 65 times the density of air at Earth's sea level, that even a sluggish wind carries enormous kinetic energy per unit area. A breeze of 3 kilometers per hour on Venus would push against your body with a force comparable to a moderate current in a terrestrial river. Moving objects on the surface would experience drag forces completely out of proportion to the apparent wind speed. This is one of the details that makes Venus particularly insidious. Even the aspects that sound mild on paper, slow winds, dim lighting, a solid rocky surface underfoot, become hostile when filtered through the physical conditions of the lower atmosphere. Nothing on Venus is what it seems at first hearing. That density also transforms the acoustic environment. sound travels differently through a medium this thick. On Earth, sound waves propagate through air at roughly 343 meters per second. On Venus, the speed of sound is significantly higher because the dense atmosphere transmits acoustic vibrations more efficiently. Frequencies shift. A human voice on Venus would sound deeper, distorted, almost unrecognizable. Not that any human vocal cord could function in an atmosphere of superheated carbon dioxide. The Venera 13 and 14 landers carried microphones that recorded audio during their brief time on the surface, making them the first spacecraft in history to capture sound from the surface of another planet, preceding the Mars microphone recordings by decades. The recordings were short and dominated by mechanical noise from the spacecraft itself, by the sound of wind moving past the hull, and by the drilling arms sampling soil. But the data confirmed that acoustic transmission on Venus follows the predicted pattern for a supercritical density atmosphere. Venus is not silent. It has a soundscape. It is just one that nothing biological could ever hear, because the medium that carries the sound would kill any listener before the first vibration reached them. The surface itself, mapped in extraordinary detail by NASA's Magellan spacecraft between 1990 and 1994, using synthetic aperture radar, is dominated by volcanic terrain. Magellan's radar penetrated the cloud layer and produced global maps revealing a world of vast basaltic plains, enormous shield volcanoes, unique geological features called coronae, which are large circular structures formed by upwelling and collapse of the crust, and elevated highland regions called tesserae that display complex, deformed terrain some scientists have compared to the oldest continental rocks on Earth. Approximately 80% of the surface is covered by volcanic plains of relatively recent geological age. Impact craters exist, but they are distributed in a pattern that tells a striking and unusual story. Venus has approximately 1,000 craters scattered across its surface. That number is far fewer than would be expected for a world the size of Venus over 4.5 billion years of bombardment history. For comparison, the Moon's surface is saturated with craters of all sizes, preserving impacts dating back billions of years. Mars carries extensive cratering records across its ancient southern highlands. Venus has almost none of this accumulated history. Its crater population is modest, and more importantly, the craters are distributed in a pattern that is statistically almost random, showing no regions that are systematically more or less cratered than others. This randomness is itself extraordinary. On most planetary bodies, older surfaces accumulate more craters, while younger surfaces have fewer. The variation in crater density is what allows scientists to estimate the relative ages of different terrains. On Venus, that variation is nearly absent, which implies something dramatic. The entire surface appears to be roughly the same geological age, somewhere between 300 million and 700 million years old. The most widely cited interpretation is that Venus experienced a catastrophic global resurfacing event, a period of planet-wide volcanic activity that repaved the entire surface with fresh lava, erasing virtually all evidence of earlier geological history. The exact timing and mechanism of this resurfacing event remain debated, but the implication is striking. Venus did not simply become hostile and then freeze in place. It actively rebuilt its own surface on a timescale that, in geological terms, is not ancient. There is another anomaly in the crater record that reinforces the atmosphere's destructive power. Venus has almost no small craters. On the Moon and Mars, small impacts are far more common than large ones, and the size distribution of craters follows a predictable curve reflecting the size distribution of impacting objects. On Venus, craters smaller than roughly 3 kilometers in diameter are essentially absent. This is not because small objects never struck Venus. It is because the atmosphere destroyed them before they could reach the ground. A meteoroid that would punch through Earth's relatively thin atmosphere and carve a modest crater has no chance of surviving descent through Venus's crushing carbon dioxide envelope. The dense atmosphere acts as a shield, shredding and decelerating small impactors through aerodynamic stress and thermal ablation until they disintegrate into fragments too small to form recognizable craters. Only the largest, most massive objects carry enough momentum to punch through the full depth of the atmosphere and strike the surface intact. The atmosphere of Venus does not merely trap heat and crush landers, it physically destroys incoming objects from space. Even rocks travelling at tens of kilometers per second are not fast enough, not massive enough, to survive the descent intact unless they exceed a certain size threshold. The sky above Venus is not just hostile, it is a weapon that has been operating continuously for billions of years, erasing small impacts from the geological record before they can be written. And the rebuilding may still be happening. In 2023, a team led by Robert Herrick of the University of Alaska Fairbanks reanalyzed Magellan radar images taken 8 months apart in the early 1990s and identified changes in a volcanic vent associated with Mart Mons, one of Venus's largest volcanoes. The vent had expanded and appeared to have been flooded with fresh lava between the two observations. This was the first direct evidence of an active volcanic eruption on Venus, observed in spacecraft data. Then, in 2024, an Italian research team led by Davide Solcanese published a study in Nature Astronomy, identifying evidence of new lava flows in 2 additional regions, Sif Mons and Niobe Planitia, detected through changes in radar backscatter between successive Magellan mapping passes. The researchers interpreted these changes as fresh rock surfaces consistent with recently solidified lava flows. Solcanese and his colleagues concluded that volcanic activity on Venus may be comparable in scale to volcanic activity on Earth. Venus is not a dead world. It is a geologically active world producing fresh volcanic terrain, venting gases into an atmosphere already loaded with sulfur compounds and carbon dioxide, and maintaining the chemical and thermal conditions that make the surface so lethal. This detail is important because it changes the character of the threat. A hostile world that is geologically dead is a relic. It reached its terminal state at some point in the past and now simply persists, gradually losing heat to space over billions of years. You can think of it as a closed case. But a hostile world that is geologically alive is a different thing entirely. Venus is actively maintaining its own hostility. Volcanoes are injecting sulfur dioxide into the atmosphere, replenishing the sulfuric acid clouds. Volcanic outgassing is contributing carbon dioxide to an atmosphere that is already 96.5% carbon dioxide. The planet is not merely hostile, it is self-reinforcing. The processes that made Venus what it is are still operating, still cycling, still sustaining the conditions that destroy every instrument we send. Consider the combined picture. Start at the top and work downward. First, a permanent global layer of sulfuric acid clouds dense enough to completely obscure the surface from space, raining acid that evaporates before it lands. Below that, an atmosphere of nearly pure carbon dioxide, extending 48 kilometers to the ground, increasing in temperature and pressure with every kilometer of descent. Winds at the cloud tops exceeding 300 kilometers per hour, circling the planet in 4 days through a mechanism that is still not fully understood. Below the clouds, a clear but increasingly dense and hot lower atmosphere, where carbon dioxide transitions into a supercritical fluid. At the surface, a temperature of approximately 465 degrees Celsius and a pressure of 92 bar, stable across the entire planet, day and night, pole to pole, on a world that rotates so slowly, a single solar day lasts 4 Earth months. Winds that are slow but carry enormous force due to the density of the surrounding medium. An atmosphere dense enough to shred incoming meteoroids and erase small impact craters from the geological record entirely. A surface dominated by volcanic terrain that shows evidence of ongoing eruption and planetary scale resurfacing. Trace chemistry that includes sulfur dioxide, hydrogen sulfide, and carbonyl sulfide in an atmosphere already dominated by the most potent greenhouse gas known to planetary science. No single one of these conditions, taken in isolation, would be unprecedented. There are hotter surfaces in the solar system. The sunlit side of Mercury can reach 430 degrees Celsius. There are higher pressures. The interiors of gas giants exceed millions of bar. There are more chemically hostile environments. Titan's surface chemistry involves liquid methane and ethane at temperatures approaching negative 180 degrees Celsius. But no other known world combines this particular set of conditions at this scale, at this intensity, all operating simultaneously across the entire planet with no reprieve. No seasonal variation, no safe zone, no gap in the clouds, no sheltered valley, no temperate latitude. Venus is not hostile in one dimension. It is hostile in every dimension at once. Temperature, pressure, chemistry, atmospheric density, cloud composition, geological activity, wind dynamics. Each layer compounds the one beneath it. Each system reinforces the others. The result is not a world with a dangerous feature. The result is a world where the entire planetary environment, from the cloud tops to the core, functions as a single integrated system of destruction. This is what the Soviet engineers were up against when they designed the Venera landers. They were not engineering for one extreme. They were engineering for all of them simultaneously. The landers had to survive descent through sulfuric acid clouds that would corrode exposed metal surfaces. They had to withstand external pressures that increased continuously during descent, reaching 92 bar at the surface. They had to function at temperatures that would disable conventional electronics within minutes. They had to transmit radio signals upward through an atmosphere so dense that radio propagation was significantly attenuated. And they had to accomplish all of this long enough to collect meaningful scientific data and relay it to an orbiting spacecraft overhead. The later Venera landers were built more like deep-sea submersibles than like anything that had previously been sent to another planet. Their pressure hulls were made of titanium, their internal electronics were sealed inside hermetically closed compartments and pre-cooled before atmospheric entry using circulating refrigerant. Circuit boards were fabricated from ceramic rather than plastic to resist thermal degradation. Camera systems were designed around mechanical scanning mirrors rather than the solid-state imaging chips that would become standard in later decades. Because solid-state electronics were too vulnerable to the heat, every component was selected and tested for survival in an environment that combined conditions found in no single location on Earth. The closest terrestrial analogy would be the inside of a high-pressure industrial autoclave filled with a hot acidic gas mixture, except the autoclave is the size of a planet and there is no off switch. Venera 13, the most successful surface mission, transmitted data for 127 minutes. Its design lifetime was 32 minutes. The fact that it exceeded that by nearly a factor of 4 was celebrated as a triumph of engineering, and it was. But the framing reveals something important about Venus. A mission where surviving for 2 hours is considered a miraculous success is a mission to a place that operates at the outer boundary of what human technology can endure. We have rovers on Mars that have functioned for years. We have orbiters around Saturn and Jupiter that operated for over a decade. We have a helicopter on Mars that exceeded its design mission by thousands of %. These achievements reflect the relative hospitality of those environments. They are cold, they are distant, they are airless or gas-shrouded, but they do not actively destroy hardened machines in minutes. Venus does. Venus has destroyed every surface lander ever sent to it. The longest any machine has survived on the surface is 2 hours and 7 minutes. That window is shorter than a typical commercial airline flight. It is shorter than most feature-length films. It is shorter than a standard high school class day. In that window, everything a lander could possibly achieve had to be achieved, because there would be no second chance, no system reset, no repair mission. The planet would consume the machine, and the machine would go silent, and the data it managed to transmit in those frantic final minutes would be all that humanity would ever recover from that particular attempt to touch the surface of Venus. No human has ever been to Venus. No human mission to Venus's surface has ever been seriously proposed. The engineering challenges are not merely extreme. They are, with current and foreseeable technology, effectively insurmountable for a crewed mission. You cannot air condition a spacecraft against an external temperature of 465 degrees Celsius sustained indefinitely. You cannot build a habitat that withstands 92 bar of external pressure without resembling a deep ocean research vessel, and deep ocean research vessels are not designed to also resist 465 degrees Celsius. The combination of temperature and pressure alone eliminates any near-term possibility of human surface exploration. Add the sulfuric acid clouds, the corrosive trace chemistry, the lack of breathable atmosphere, and the absence of accessible water, and you arrive at a world that is not merely inhospitable but almost definitionally incompatible with human presence. Mars, by comparison, is practically welcoming. Mars is cold, with surface temperatures that average approximately -60 degrees Celsius. It has a thin atmosphere of carbon dioxide at roughly 1% of Earth's sea level pressure. It has dust storms and high radiation levels due to its thin atmosphere and lack of global magnetic field. But humans can, in principle, insulate against cold. They can pressurize habitats against a near vacuum much more easily than against a crushing high-pressure atmosphere. They can shield against radiation. Mars is difficult. Mars is dangerous. Mars is, with sufficient technology and resources, potentially survivable. Venus is not. Venus occupies a different category entirely. It is a world where the environment actively and comprehensively exceeds the tolerance of every material, every system, and every biological process that human engineering or human biology can currently sustain. And yet this world is not distant. It is not tucked away in the outer solar system behind a shield of cold and distance. Venus is right next door. At closest approach, it is the nearest planet to Earth. You can see it tonight if the sky is clear. It is the bright, steady, beautiful point of light hanging in the west after sunset, or rising in the east before dawn, depending on where it sits in its orbit. The ancients called it the morning star, the evening star, the jewel of the sky. It is radiant precisely because its sulfuric acid clouds reflect so much sunlight, the same clouds that seal in the heat, maintain the pressure, and shroud the catastrophe below. Venus is beautiful to look at from a distance. It is a death sentence up close. The most advanced robotic lander humanity has ever sent to this beautiful, nearby world survived for 2 hours and 7 minutes before the planet destroyed it. Nothing we have built has done better. Nothing we can currently build would do significantly better. The surface of Venus remains, more than 40 years after the last successful landing, one of the least explored and most hostile frontiers in all of planetary science. The obvious question is no longer what Venus is like. The Venera landers, the Magellan radar maps, the Pioneer Venus atmospheric probes, and decades of telescopic observation have given us a thorough, precise, and terrifying inventory of conditions. The obvious question now is the one that transforms Venus from a catalogue of extremes into something much more unsettling. How did this happen? How did a planet so similar to Earth in size, mass, density, and composition become the most hostile rocky surface in the solar system? The answer lies not in what Venus is, but in what Venus was, and in a process that began billions of years ago with conditions that would have looked, to any observer, remarkably like home. 4.5 billion years ago, there was no obvious reason to predict that Venus and Earth would end up differently. Both planets formed from the same rotating disk of gas and dust that surrounded the young sun. Both accreted from the same pool of silicate rock, iron, and volatile compounds. Both were large enough to retain thick atmospheres through gravitational capture of outgassed volatiles. Both were close enough to the sun to be warm, but not so close that their early chemistry would be dominated by the extreme radiation environment that stripped Mercury down to a dense, airless remnant. If you could have observed the inner solar system roughly 4 billion years ago, you would have seen two young rocky worlds of nearly identical size, both volcanically active, both wrapped in thick early atmospheres rich in carbon dioxide and water vapor, both cooling from the violence of their formation. You would have seen what looked like two versions of the same experiment running side by side. One of those experiments would go on to develop stable liquid oceans, a carbon cycle that regulated atmospheric composition over geological time, plate tectonics that recycled crustal material, a magnetic field that shielded the atmosphere from solar wind stripping, and eventually, biology. The other would become Venus. The divergence begins with a number that sounds almost trivially small. Venus orbits the Sun at an average distance of approximately 108 million kilometers. Earth orbits at approximately 150 million kilometers. The difference is roughly 42 million kilometers, which in solar system terms is modest. Mars, for comparison, orbits at approximately 228 million kilometers from the Sun, nearly 80 million kilometers farther out than Earth. Venus is closer to Earth's orbit than Mars is, sitting only about 30% closer to the Sun than we do. But that 30% matters enormously for one specific reason. The intensity of solar radiation follows an inverse square law. Move 30% closer to the Sun, and you do not receive 30% more energy. You receive roughly 90% more energy at the top of your atmosphere. Venus receives approximately 1.9 times the solar flux that Earth does, nearly double the sunlight per unit area, falling on a planet that is, in every structural respect, almost identical to ours. On modern Venus, this would not matter much in isolation, because the planet's extraordinarily high albedo, its reflectivity, sends roughly 75% of that incoming sunlight back into space before it ever penetrates the clouds. Venus actually absorbs less total solar energy than Earth does. The modern Venusian climate is not maintained by direct solar heating. It is maintained by the greenhouse effect operating through an atmosphere so loaded with carbon dioxide that it traps virtually all outgoing infrared radiation from the surface. But the modern atmosphere is the end state, not the starting condition. The question is, what happened at the beginning, when Venus was young and its atmosphere was still evolving, and when the difference in solar input may have tipped the planet onto a path from which there was no return? The leading scientific model for how Venus became what it is today centers on a concept called the runaway greenhouse effect. This is a specific physical process with a precise meaning in planetary science, not merely a colloquial way of saying things got very hot. The runaway greenhouse effect occurs when a planet's surface temperature rises to the point where water can no longer remain liquid on the surface. As the surface warms, more water evaporates into the atmosphere. Water vapor is a powerful greenhouse gas, far more effective per molecule at trapping infrared radiation than carbon dioxide. More water vapor in the atmosphere traps more heat, which raises the surface temperature further, which evaporates more water, which traps more heat. The feedback is positive and self-amplifying. Once it begins, it does not stabilize at a new, slightly warmer equilibrium the way moderate greenhouse warming does on Earth. It accelerates. The surface temperature rises continuously until all surface water has evaporated into the atmosphere. At that point, the planet has lost its liquid water entirely, and the atmosphere is loaded with steam, which continues trapping heat at extreme efficiency. On Earth, this feedback loop is held in check by a combination of factors. Our distance from the Sun means that the equilibrium surface temperature, even with moderate greenhouse warming, allows water to condense and remain liquid on the surface. Liquid water enables the carbonate-silicate cycle, a geological thermostat that regulates atmospheric carbon dioxide over millions of years. When carbon dioxide levels rise and temperatures increase, chemical weathering of silicate rocks accelerates. Rainwater, made slightly acidic by dissolved atmospheric carbon dioxide, reacts with exposed rock surfaces, producing dissolved bicarbonates and silicates that are carried by rivers to the oceans. In the oceans, these dissolved compounds combine with calcium to form calcium carbonate, limestone, which settles to the ocean floor and is eventually subducted into the mantle through plate tectonics. This process removes carbon dioxide from the atmosphere and sequesters it in rock. When carbon dioxide levels drop and temperatures fall, weathering slows, volcanic outgassing gradually restores carbon dioxide to the atmosphere, and temperatures rise again. The cycle oscillates over geological time, keeping atmospheric carbon dioxide and surface temperature within a range that permits liquid water to persist. Earth has maintained this balance for at least 3.5 billion years, possibly longer. Venus had no such luck. The prevailing hypothesis, supported by decades of climate modelling, proposes that Venus's slightly closer proximity to the Sun meant that during the planet's early history, the surface was warm enough to keep water vapor in the atmosphere at concentrations significantly higher than on early Earth. Even a modest initial temperature difference of a few tens of degrees could have been enough. More atmospheric water vapor meant a stronger greenhouse effect. A stronger greenhouse effect meant higher surface temperatures. Higher temperatures meant more evaporation. The loop engaged. Unlike on Earth, where ocean condensation and the carbonate-silicate cycle could counteract the warming, Venus had no mechanism powerful enough to arrest the feedback once it passed a critical threshold. The surface warmed until every reservoir of liquid water had been evaporated into the atmosphere. The oceans, if they had ever existed, boiled away. The sky filled with steam. the surface temperature soared, but the loss of the oceans was not the end of the catastrophe. It was the beginning of a second, equally devastating phase. Without liquid water on the surface, the carbonate-silicate cycle could not function. There were no rivers to carry dissolved minerals to the sea. There was no sea to accumulate carbonate sediments. There was no mechanism to pull carbon dioxide out of the atmosphere and lock it into rock. Meanwhile, volcanoes continued erupting, as they do on any geologically active world, releasing carbon dioxide and sulfur compounds into the atmosphere. On Earth, volcanic carbon dioxide is balanced by weathering and ocean absorption on timescales of hundreds of thousands of years. On Venus, with no water to drive weathering and no ocean to serve as a carbon sink, every molecule of volcanic carbon dioxide that entered the atmosphere stayed there, permanently. Over hundreds of millions of years, this one-way accumulation transformed Venus's atmosphere into what we observe today. Carbon dioxide built up relentlessly, thickening the atmosphere, increasing the surface pressure, and strengthening the greenhouse effect with every increment. The atmosphere became a thermal blanket, so massive and so opaque to infrared radiation that surface temperatures climbed to their current value of approximately 465 degrees Celsius and stabilized there, not because the warming stopped, but because the system reached a new equilibrium where the planet radiates exactly as much energy back into space as it absorbs from the sun. That equilibrium just happens to be at a temperature that melts lead. The water vapor that once filled the upper atmosphere did not remain there indefinitely. In the upper reaches of Venus's atmosphere, solar ultraviolet radiation broke water molecules apart into hydrogen and oxygen atoms through a process called photodissociation. Hydrogen, being the lightest element, escaped into space. It was too light for Venus's gravity to retain at the temperatures present in the upper atmosphere. Over geological timescales, this hydrogen loss was essentially irreversible. The oxygen left behind likely reacted with surface minerals and atmospheric compounds, being absorbed rather than accumulating as free oxygen. The net result was the permanent destruction of Venus's water inventory. The planet did not merely lose its oceans to evaporation. It lost the hydrogen atoms that would have been necessary to ever reconstitute those oceans. The water was not hidden or stored somewhere on Venus. It was dismantled molecule by molecule and scattered into space. The loss is permanent on any timescale relevant to planetary science. Evidence for this ancient water loss persists in Venus's atmosphere today. The ratio of deuterium to ordinary hydrogen in Venus's atmosphere is approximately 100 to 150 times higher than the same ratio on Earth. Deuterium is a heavier isotope of hydrogen, containing one proton and one neutron instead of just one proton. Because it is heavier, deuterium escapes to space more slowly than ordinary hydrogen. Over billions of years of atmospheric loss, the lighter hydrogen was preferentially stripped away, leaving the atmosphere enriched in the heavier deuterium. This enrichment is one of the strongest pieces of evidence that Venus once had significantly more hydrogen, and therefore significantly more water, than it does today. The exact amount of original water remains debated. Some estimates suggest Venus may have had enough water to cover the entire surface to a depth of several meters. Others, based on more recent models, suggest the initial water inventory could have been much larger, potentially comparable to a shallow ocean. The deuterium ratio cannot tell us precisely how much water existed, but it confirms that whatever amount was present has been overwhelmingly lost through a process consistent with long-term atmospheric escape. This is where the scientific debate becomes genuinely fascinating and where precision matters most in distinguishing confirmed observations from competing hypotheses. The Runaway greenhouse model described above is the leading framework for understanding Venus's climate history, but significant questions remain about the timeline, the initial conditions, and whether Venus ever had the stable liquid oceans that the model in its strongest form implies. One influential line of research, led by Michael Way and Anthony Del Genio at NASA's Goddard Institute for Space Studies, has used general circulation models adapted from Earth climate simulations to explore whether Venus could have maintained habitable surface conditions for an extended period. Their results, published in 2016 and expanded in subsequent studies, suggest that if Venus had a shallow liquid ocean covering a portion of its surface, and if it rotated slowly, as it does today, atmospheric circulation patterns would have produced thick dayside cloud cover that reflected enough sunlight to keep surface temperatures moderate. Under these conditions, their models indicate Venus could have remained habitable for up to 2 billion years, possibly even 3 billion, before some catastrophic event tipped the climate past the point of no return. They proposed that simultaneous eruptions of massive volcanic provinces, similar to large igneous provinces on Earth but occurring together rather than sequentially, could have injected enough carbon dioxide into the atmosphere to overwhelm the planet's weakened climate regulation and trigger the final runaway. This is a remarkable hypothesis because it implies that Venus may have been a habitable world for the majority of its history, losing its oceans and collapsing into its current state relatively recently in geological terms, perhaps within the last 700 million to 1 billion years. If true, it means the catastrophe was not inevitable from the start. It means Venus may have spent billions of years as a potentially life-bearing world before a geological event tipped it over the edge. This would make the runaway greenhouse not just a story about planetary formation, but a story about planetary fragility, about how even a world with stable oceans and moderate temperatures can lose everything if conditions change faster than the climate system can compensate. However, competing research challenges this timeline. A study published in Nature in 2021 by Martin Turbet and colleagues at the University of Geneva used three-dimensional climate models to examine whether water vapor on early Venus could have condensed into surface oceans in the first place. Their results suggested that on a young Venus, receiving more solar energy and surrounded by a thick, early atmosphere, cloud formation patterns would have been fundamentally different from the way in Del Genio models. Specifically, they found that clouds would preferentially form on the night side of the planet rather than the day side, meaning they would not reflect enough sunlight to cool the surface sufficiently for water to condense. Under this scenario, Venus was hot and dry from very early in its history. The water delivered during formation remained as steam in the atmosphere and was gradually lost to space through photodissociation and hydrogen escape without ever forming surface oceans. Venus in this model was never habitable. It never had a temperate period. The runaway greenhouse was not a late catastrophe but an initial condition that the planet never escaped. Both positions remain scientifically credible. Neither has been definitively confirmed or refuted. The difference between them is profound. In one version of Venus's history, a world with oceans and possibly life was destroyed by a geological catastrophe that overwhelmed a functioning climate system. In the other, Venus was doomed from the beginning, born too close to the Sun to ever stabilize liquid water on its surface. Both versions end in the same place, the Venus we observe today, but they carry very different implications for how we think about planetary habitability and the fragility of climate systems. Resolving this debate is one of the primary objectives of the planned Venus missions of the next decade, including NASA's Da Vinci probe, which would directly sample the composition of Venus's lower atmosphere and measure noble gas ratios that can distinguish between these formation scenarios. Regardless of which timeline proves correct, one feature of Venus's current state is unambiguous. The planet has no global magnetic field. Earth's magnetic field is generated by the convective motion of liquid iron in the outer core, a process called the geodynamo. This field extends far into space, creating a magnetosphere that deflects the solar wind, the stream of charged particles continuously emitted by the Sun. Without this magnetic shield, the solar wind directly impacts the upper atmosphere, stripping away light gases over time. Venus lacks this protection. The European Space Agency's Venus Express mission, which orbited the planet from 2006 to 2014, directly measured the rate at which the solar wind is stripping ions from Venus's upper atmosphere. The measurements confirmed that hydrogen and oxygen ions are being lost at measurable rates, even today, billions of years after the bulk of the water was lost. Why Venus lacks a magnetic field is itself an open question. One possibility is that Venus's core has cooled to the point where convection has largely ceased. Another is that the core never developed the conditions necessary for a sustained dynamo, perhaps because Venus's slow rotation or different internal thermal history prevented the convective patterns required. Some researchers have linked the absence of plate tectonics on Venus to the absence of a magnetic field, suggesting that stagnant lid tectonics, where the entire crust forms a single immobile plate rather than multiple recycling plates, may reduce the rate of heat loss from the interior and suppress core convection. This is speculative, and the true explanation awaits better constraints on Venus's internal structure. The absence of a magnetic field compounds the atmospheric catastrophe. Not only did Venus lose its water through greenhouse-driven evaporation and photodissociation, but the solar wind continues to erode the upper atmosphere, ensuring that any water vapor that might somehow be reintroduced would be progressively stripped away. Venus's current atmospheric water vapor content is measured in parts per million. This is not a dry climate. This is a planet where water has been functionally eradicated from the surface environment and is being actively removed from the upper atmosphere by the sun itself. But the magnetic field is not the only deep interior system that failed on Venus. Plate tectonics, the process that continuously reshapes Earth's surface and drives the long-term carbon cycle, also appears to be absent. On Earth, the lithosphere is broken into roughly 15 major plates that move relative to one another, driven by convective currents in the underlying mantle. At divergent boundaries, fresh basaltic crust forms as plates pull apart. At convergent boundaries, old oceanic crust is pushed beneath continental plates in a process called subduction, carrying with it the carbonate sediments that accumulated on the ocean floor over millions of years. These carbonates descend into the mantle, where heat and pressure decompose them, releasing carbon dioxide that eventually returns to the atmosphere through volcanic outgassing. This subduction step is not a minor detail. It is the physical engine that completes the carbonate-silicate cycle. Without subduction, carbon locked into sedimentary rock has no return pathway. The geological thermostat has no reset mechanism. Weathering can pull carbon dioxide out of the atmosphere and deposit it in ocean floor carbonates, but without subduction to recycle those carbonates back into the mantle, the cycle eventually stalls. Venus has none of this. Its surface shows no evidence of the linear mountain chains, deep ocean trenches, or mid-ocean ridges that characterize plate boundaries on Earth. Instead, Venus appears to operate under what geophysicists call a stagnant lid regime. The entire lithosphere forms a single rigid shell over the mantle, unbroken by the systematic plate boundaries that define Earth's tectonic system. Heat from the interior cannot escape continuously through spreading ridges and subduction zones the way it does on Earth. Instead, it builds up beneath the stagnant lid, accumulating over hundreds of millions of years until the thermal pressure becomes unsustainable. At that point, the lithosphere may fail catastrophically, producing the kind of planet-wide volcanic resurfacing event that the crater record reveals. The event that appears to have repaved Venus's entire surface somewhere between 300 million and 700 million years ago. This is not gradual recycling. It is episodic, catastrophic overturn, a fundamentally different mode of planetary geological evolution that releases enormous volumes of volcanic gas in relatively short bursts, rather than venting it steadily over time. The consequences for atmospheric carbon are severe. On Earth, the continuous tectonic cycle acts as a slow, steady valve, releasing carbon dioxide through volcanism and recapturing it through subduction at rates that roughly balance over geological time. On Venus, with no subduction to recycle surface carbonates and no ocean to form those carbonates in the first place, every molecule of volcanic carbon dioxide is a permanent atmospheric addition. The stagnant lid does not merely prevent carbon recycling, it ensures that when volcanic outgassing does occur, particularly during catastrophic resurfacing episodes, the atmospheric impact is enormous and irreversible. Venus lost its water, lost its weathering cycle, and lost its tectonic recycling system. 3 failures, each reinforcing the others, each sealing the planet more completely into the state we observe today. Now consider the Earth-Venus comparison in its most unsettling form. Earth's atmosphere contains approximately 420 parts per million of carbon dioxide today. Venus's atmosphere is approximately 96.5% carbon dioxide. These numbers seem incomparable, but total inventory tells a different story. Earth has enormous reserves of carbon dioxide locked away in carbonate rock, limestone, marble, chalk, and other sedimentary formations deposited over billions of years by the carbonate-silicate cycle operating through liquid oceans. If you were to heat Earth's crust sufficiently to decompose all of that carbonate rock and release the carbon dioxide back into the atmosphere, the total amount of carbon dioxide liberated would be approximately 60 to 80 bar of atmospheric pressure. Add the carbon dioxide currently dissolved in the oceans, and the total approaches 90 bar. Venus's surface pressure is approximately 92 bar, almost entirely carbon dioxide. The implication is staggering. Earth and Venus may have started with very similar total inventories of carbon dioxide. The difference is not in how much carbon each planet possesses. The difference is in where that carbon sits. On Earth, the vast majority is safely sequestered in rock and dissolved in ocean water, held in check by the carbonate-silicate cycle, by liquid water, by plate tectonics, by a functioning geological thermostat that has operated continuously for billions of years. On Venus, all of that carbon is in the atmosphere, every molecule of it. There is no ocean to absorb it. There is no weathering cycle to lock it into rock. There is no plate tectonic system to subduct carbonate sediments into the mantle. Every atom of carbon that volcanic activity released into Venus's atmosphere over the last 4 billion years remains there today, pressing down on the surface with 92 times the weight of Earth's atmosphere, trapping heat with an efficiency that no other planetary atmosphere in the solar system can match. This comparison reframes the entire Venus story. The terror of Venus is not that it is alien. It is that it is familiar. The same element that makes up the bulk of Venus's crushing, superheated atmosphere exists on Earth in almost exactly the same quantity. The difference between our world and the most hostile, rocky surface in the solar system is not the amount of carbon dioxide each planet possesses. It is the fact that on Earth, most of that carbon dioxide is locked safely away in rock and water, and on Venus, it is not. Earth did not avoid Venus's fate because it has less carbon. It avoided Venus's fate because it has oceans. Oceans that exist, in part, because Earth is roughly 30% farther from the Sun. 30%, that is the margin. That is the distance, in astronomical terms almost negligibly small, that separates a planet with stable liquid water, a functioning carbon cycle, and the conditions necessary for life from a planet where the surface melts lead, the atmosphere crushes spacecraft, and every drop of water has been dismantled and lost to space. The orbital distance between Venus and Earth is smaller than the distance separating Earth from Mars. Two worlds made of the same material, formed at the same time, nearly the same size, carrying nearly the same carbon inventory, separated by less than 42 million kilometers of orbital distance. One became a biosphere, the other became an incinerator. This is the fact that elevates Venus from a hostile planet to something that feels, in a way that is difficult to articulate precisely but impossible to ignore, like a warning, not a metaphorical warning, not a rhetorical device, a physical one, written in 465 degrees of surface temperature, 92 bar of atmospheric pressure, and a deuterium to hydrogen ratio that records the destruction of an entire planetary water supply. Venus is a world-sized record of what happens when the conditions that keep a terrestrial planet habitable fail. And those conditions, liquid water, carbonate weathering, ocean absorption, plate tectonics, are not guaranteed features of rocky planets. They are contingencies. They are outcomes that depend on orbital distance, atmospheric composition, volcanic history, magnetic field strength, and the interactions between all of these variables over billions of years. Earth has all of them. For now. Venus had some of them, possibly all of them, and lost every single one. The mechanisms that destroyed Venus's habitability are not exotic. They are physics and chemistry operating at planetary scale over geological time. The runaway greenhouse is not a fantasy. It is a physical process with clear thermodynamic thresholds that has been modelled, studied, and to the extent that Venus constitutes a natural experiment, observed. The carbon cycle failure that loaded Venus's atmosphere with 92 bar of carbon dioxide is not a freak occurrence. It is what happens to any terrestrial planet that loses its liquid water before its volcanic activity ceases. The question that remains, the question that transforms this story from planetary science into something that presses against the boundaries of human self-awareness, is what Venus means, not what it is. We know what it is, not how it got there. We have credible models, competing but converging, for how it reached this state. The question is what it means that a planet this similar to ours, this close to ours, ended up this way. And the answer to that question is not scientific. It is something else entirely. Venus is visible tonight. If you are hearing this after sunset and the sky is clear, step outside and look toward the west. The brightest point of light above the horizon, steady and unwavering, not twinkling the way stars do, is Venus. It outshines everything in the night sky except the moon. Ancient civilizations built calendars around it. Poets wrote about it. Navigators steered by it. It is so bright and so beautiful that for most of human history, it was given two separate names: the morning star when it appeared before dawn, and the evening star when it lingered after sunset, because people could not believe the same object could be responsible for both apparitions. Venus is the most visible planet in our sky. It is the closest planet to our world. And it is, as we have now seen, the most comprehensively hostile rocky surface ever measured by human instruments. That combination, the beauty, the proximity, the familiarity of its size and mass and composition, set against the absolute lethality of its surface environment, is what makes Venus not merely interesting or extreme, but genuinely terrifying in a way that no other planet in the solar system can match. But to leave it there, to conclude simply that Venus is very hot and very hostile and very close, would miss the deeper point. Venus is not terrifying because it is hostile. Plenty of places in the solar system are hostile. Venus is terrifying because it is a record. A physical, measurable, chemically precise record of how a world that should have been one of the most Earth-like planets in existence became instead a planetary catastrophe. And that record is not locked away in some abstract data set. It is written across every layer of the planet, from the sulfuric acid cloud tops to the superheated basaltic surface, in a language that planetary scientists can read and that carries implications no one studying Earth's climate can entirely ignore. The planned missions of the next decade represent humanity's most serious attempt in a generation to read that record in detail. In 2021, NASA selected 2 Venus missions as part of its Discovery program. Da Vinci, the deep atmosphere Venus investigation of noble gases, chemistry, and imaging, would send an orbiter and an atmospheric descent probe to Venus. The probe would fall through the atmosphere over approximately 1 hour, sampling gases at every altitude, measuring noble gas isotope ratios that can distinguish between competing models of Venus's formation and water loss history, capturing high-resolution images of the surface during descent through the lowest cloud layers, and collecting data on atmospheric chemistry in the deep lower atmosphere that has not been directly sampled since the Soviet Venera missions of the 1980s. Da Vinci is designed to answer the question that the history of Venus leaves open. Did Venus once have liquid water on its surface? And if so, when and how did it lose that water? The noble gas ratios, particularly the ratios of xenon isotopes, and the precise measurement of the deuterium to hydrogen ratio at multiple atmospheric levels, can provide constraints that no orbital observation can match. This would be the first American spacecraft to enter Venus's atmosphere since the Pioneer Venus multiprobe in 1978, nearly half a century ago. Veritas, the Venus emissivity, radio science, INSAR, topography, and spectroscopy mission would orbit Venus and map its surface using synthetic aperture radar at resolutions far exceeding anything achieved by Magellan. Where Magellan produced global maps with a resolution of roughly 100 to 300 meters per pixel, Veritas would achieve resolutions on the order of 15 to 30 meters. This leap in detail would transform our understanding of Venus's geological history, revealing whether the Tesserae highlands preserve evidence of ancient water erosion, mapping active volcanic regions in real time by detecting surface changes between orbital passes, and measuring surface emissivity at near-infrared wavelengths to determine rock composition. Veritas would effectively give scientists their first detailed geological portrait of Venus, turning a world known primarily through coarse radar sketches into a planet whose surface history can be read with the precision currently reserved for Mars and the Moon. The European Space Agency's Envision orbiter, which began construction in 2025 with a launch target no later than 2033, would complement both NASA missions. Envision carries a suite of instruments designed to study Venus's surface, subsurface, and atmosphere from orbit, including a radar provided by NASA and a sounder capable of probing beneath the surface to detect layered geological structures. Together, these three missions would constitute the most comprehensive investigation of Venus ever attempted, a coordinated campaign to understand how and why the planet diverged from Earth. The effort is not limited to the United States and Europe. India's space agency, ISRO, has been developing a Venus orbiter mission called Shukrayan, named after the Sanskrit word for Venus. The mission is designed to carry 16 scientific payloads, including a synthetic aperture radar, a thermal camera, and instruments to study atmospheric composition and the interaction between Venus's atmosphere and the solar wind. Shukrayan would also serve as a technology demonstration for aerobraking, using atmospheric drag to gradually lower its orbit rather than relying entirely on onboard fuel. If the mission proceeds as planned, it would contribute a significant additional dataset to the International Venus Campaign, particularly regarding upper atmosphere dynamics and the mechanisms of ongoing atmospheric escape. Venus has not been studied by an Indian spacecraft before, and Shukrayan would mark the first time India's deep space capabilities are directed at a planet other than Mars or the Moon. But the future of the broader Venus campaign is uncertain. As of early 2026, NASA's Planetary Science Division faces significant budget pressure. The 2026 appropriations bill provided $99 million to continue Da Vinci development, and work on Veritas is described as ramping up slowly. However, both missions appeared on proposed cancellation lists under the administration's budget request, which sought to cut NASA's planetary science funding by roughly 24%. Louise Proctor, director of NASA's Planetary Science Division, stated publicly in March 2026 that getting all three Venus missions to continue would be a challenge. ESA's Envision depends in part on NASA's contribution of radar hardware and deep space network support, both of which face potential cuts. The so-called Decade of Venus that scientists envisioned when the missions were selected in 2021 is not guaranteed. It depends on funding decisions that remain unresolved. Meanwhile, a smaller and more unconventional mission may reach Venus first. The Venus Lifefinder, a privately funded collaboration between Rocket Lab and the Massachusetts Institute of Technology, aims to send a small probe through Venus's cloud layer to search for organic compounds and potential biosignatures. Originally planned for early 2025, the mission was delayed and is now targeting a summer 2026 launch aboard a Rocket Lab Electron vehicle. The probe would pass through the cloud layer at approximately 48 to 60 kilometers altitude, the region where temperatures and pressures are closest to Earth-like conditions, and use a laser instrument called an autofluorescing nephelometer to analyze cloud particles for the presence of complex organic molecules. This mission does not aim to characterize Venus's surface or deep atmosphere. It targets a specific and highly speculative hypothesis that has generated significant scientific debate. That hypothesis is worth addressing directly, because it illuminates something important about how we think about Venus. In 2020, a team led by Jane Greaves of Cardiff University announced the detection of phosphine gas in Venus's cloud layer using sub-millimeter wavelength telescope observations. Phosphine on Earth is primarily associated with biological processes or industrial chemistry. Its presence in Venus's clouds, if confirmed, would be difficult to explain through known abiotic chemistry, leading the team to suggest it could be a potential biosignature. The announcement generated enormous public and scientific interest, followed by equally intense scrutiny. Multiple independent teams reanalyzed the data and reached conflicting conclusions. Some could not reproduce the phosphine signal at statistically significant levels. Others identified potential calibration issues with the original observations. As of the present, the detection of phosphine on Venus remains contested and unconfirmed. It is a candidate observation, not an established finding. The scientific community has not reached consensus on whether phosphine is present in Venus's atmosphere at the concentrations originally reported. Separately from the phosphine debate, some scientists have proposed that the zone between roughly 48 and 60 kilometers altitude in Venus's atmosphere could, in principle, support microbial life. At those altitudes, Temperatures range from approximately 0 to 80 degrees Celsius, and pressures are in the range of roughly half a bar to 2 bar, conditions that overlap with environments on Earth where extremophilic microorganisms survive. The sulfuric acid concentration poses a severe challenge, but some researchers have speculated about biochemistries that could tolerate or even exploit acidic conditions. This remains a speculative hypothesis. No direct evidence of life in Venus's clouds has been found. No biological mechanism has been demonstrated that could survive the specific combination of concentrated sulfuric acid, ultraviolet radiation, and chemical conditions present at those altitudes. The hypothesis is scientifically legitimate as a topic of investigation, but it is not supported by confirmed evidence. What makes this speculation revealing is not whether it will prove correct. It is what it tells us about Venus's status in the hierarchy of planetary terror. The fact that the only potentially survivable zone on the entire planet is a narrow band of atmosphere roughly 12 kilometers thick, suspended between a layer of sulfuric acid clouds and an abyss of superheated supercritical carbon dioxide, tells you everything about the world below. Even the most optimistic interpretation of Venus's habitability potential confines the possibility of life to a sliver of atmosphere that represents an infinitesimal fraction of the planet's total volume. Below that sliver, conditions are so extreme that survival is not merely unlikely but physically impossible for any known biology. The speculation about cloud life does not soften Venus's hostility. It throws that hostility into sharper relief by showing just how narrow the margin of survivability is on a world that should, by its structural characteristics, have been one of the most hospitable planets in the solar system. This brings us to the question that Venus poses not just for planetary science, but for the study of worlds beyond our solar system. In the past 2 decades, the search for habitable exoplanets has become one of the defining scientific endeavors of the era. Thousands of exoplanets have been confirmed using transit photometry, radial velocity measurements, and direct imaging. A significant number of these planets orbit within or near the habitable zones of their host stars, the range of orbital distances where liquid water could theoretically exist on a rocky surface. When these discoveries are announced, the language is almost always hopeful. Earth-sized planet found in habitable zone, potentially habitable world discovered around nearby star. The framing assumes that a rocky planet at the right distance from its star is a candidate for habitability. Venus is a rebuke to that assumption. Venus sits near the inner edge of the Sun's habitable zone. Depending on which climate model you use and how you define the zone's boundaries, Venus may be just inside, just outside, or right on the edge of the region where liquid water could theoretically persist. And yet Venus is the least habitable rocky surface we have ever measured. Its surface conditions are so extreme that no known material can survive prolonged exposure to them without degradation. If an astronomer in another star system detected Venus using transit photometry, they would measure a planet approximately 95% the diameter of Earth orbiting a Sun-like star at a distance compatible with the inner habitable zone. Without atmospheric data, that astronomer would have no way to distinguish Venus from a potentially habitable world. Venus would look like a promising candidate. It would look like Earth. This is the exoplanet problem that Venus defines. For every rocky planet detected near the inner edge of a star's habitable zone, there is a possibility, perhaps a significant probability, that the planet is not an Earth but a Venus. A world that formed with similar materials, at a similar size, in a region that is close enough to the right temperature range to seem promising, but that crossed the threshold into runaway greenhouse conditions at some point in its history and now exists as a superheated, desiccated, pressurized nightmare. Without the ability to characterize these planets' atmospheres, something that is only now becoming possible with instruments like the James Webb Space Telescope, we cannot tell the difference. The universe may be full of Venuses masquerading as Earths, and every one of them would represent the same story, a world that could have been habitable, a world that lost everything. Astronomers have formalized this concern by defining what they call the Venus zone, a concept distinct from the habitable zone, though partially overlapping with its inner edge. The Venus zone describes the range of orbital distances where a rocky planet is more likely to have experienced a runaway greenhouse than to have maintained stable surface oceans. The boundaries depend on stellar luminosity, atmospheric composition, and planetary properties. but for a Sun-like star, the Venus zone begins roughly where Venus orbits and extends inward. Any rocky exoplanet detected within this range should be considered a Venus candidate first and an Earth candidate second, unless atmospheric observations demonstrate otherwise. The Venus zone concept emerged directly from the study of our own Venus. Without a real-world example of a runaway greenhouse planet sitting right next to a habitable one, the concept would remain purely theoretical. Venus grounds it in observation. It converts an abstract boundary condition into a measured planetary outcome. The James Webb Space Telescope is now beginning to provide the atmospheric data that could distinguish between these possibilities for the first time. JWST can detect the spectral signatures of atmospheric gases in exoplanets that transit their host stars. When a planet passes in front of its star, a small fraction of starlight filters through the planet's atmosphere. Different gases absorb light at characteristic wavelengths, leaving fingerprints in the transmitted spectrum. A carbon dioxide-dominated atmosphere with no detectable water vapor and elevated sulfur compounds would be consistent with a Venus-like world. An atmosphere containing water vapor, oxygen, ozone, or methane would point toward conditions more compatible with habitability. Early JWST results on rocky exoplanets in the TRAPPIST-1 system, and others have demonstrated that atmospheric characterization of small rocky worlds is technically achievable, though the signals are faint and require multiple transits to build statistical confidence. The technology is not yet mature enough to routinely classify planets as Earths or Venuses, but it has crossed the threshold from impossible to merely difficult. Within the next decade, astronomers expect to characterize the atmospheres of dozens of rocky exoplanets in or near habitable zones. Venus provides the template for what a failed outcome looks like. Without that template, without knowing exactly what atmospheric signature a runaway greenhouse leaves behind, the search for habitable worlds would be operating blind. Venus also defines a concept that planetary scientists call the inner edge of the habitable zone, the closest distance to a star at which a rocky planet can maintain stable liquid water on its surface over geological time. This boundary is not a sharp line. It depends on atmospheric composition, cloud cover, planetary rotation rate, volcanic activity, and other factors that vary from world to world. But Venus provides the most direct observational constraint we have. It tells us that a planet of approximately Earth's mass, orbiting approximately 30% closer to a Sun-like star, did not maintain surface habitability. Whether Venus ever had a habitable period and lost it, or whether it was never habitable at all, the end result is the same. At Venus's orbital distance, something went catastrophically wrong. This observation anchors every theoretical model of habitable zone boundaries. Venus is not just a data point, it is the data point, the nearest and most detailed example of a terrestrial planet that failed. And it failed not because it was deficient in raw materials or too small to retain an atmosphere or too far from the sun to receive energy. It failed because the delicate interplay of conditions that maintain habitability on a rocky world, liquid water, a functioning carbon cycle, atmospheric regulation, magnetic protection from the solar wind, is exactly that. Delicate. These are not robust, self-correcting systems that operate identically on every planet of the right size and distance. They are contingent outcomes that depend on initial conditions, orbital parameters, geological evolution, and the specific sequence of events that unfolds over billions of years. Earth got the right sequence. Venus did not, and the gap between the two outcomes is not a spectrum. It is a cliff. Earth sits on one side with oceans, oxygen, life, and a surface temperature that averages 15 degrees Celsius. Venus sits on the other side with no water, no oxygen, no life, and a surface temperature of 465 degrees Celsius. There is no intermediate state. There is no planet that is halfway between Earth and Venus. The runaway greenhouse is a threshold. Once crossed, the planet does not settle into a moderately uncomfortable middle ground. It falls all the way to the bottom. This is where the science becomes difficult to separate from something that feels more personal. Earth's climate system is not static. It is a dynamic, evolving system that has undergone dramatic shifts over geological time. Ice ages have come and gone. The planet has been warmer and cooler than its current state many times. Carbon dioxide levels have been higher than they are today, significantly higher during some past epochs, and the planet recovered. Earth's climate system has proven resilient over billions of years. But resilience is not invincibility. The carbonate-silicate cycle that regulates atmospheric carbon dioxide operates on timescales of hundreds of thousands to millions of years. On shorter timescales, the system can be overwhelmed if carbon dioxide is added to the atmosphere faster than weathering and ocean absorption can remove it. Venus demonstrates what the end state looks like when that regulation fails permanently. It is not a prediction for Earth. The scientific consensus is clear that Earth is not at risk of a runaway greenhouse under current or foreseeable conditions. The Sun is not yet luminous enough, and Earth's water inventory is large enough that a true runaway greenhouse, in the strict physical sense of surface temperatures rising until all oceans evaporate, is not expected for at least another billion years or more, when the Sun's gradual brightening will push the inner edge of the habitable zone outward past Earth's orbit. That is a geological timescale, not a human one. But Venus serves as a reminder that the stability we take for granted is not a permanent feature of rocky planets. It is a temporary condition maintained by a specific set of geological and atmospheric processes that operate within specific limits. Push those processes past their limits, on whatever timescale, and the consequences are not gradual, they are catastrophic. Venus is the proof, and here is where the story takes on a dimension that no amount of scientific qualification can entirely soften. The Sun is getting brighter. This is not speculation. It is a confirmed consequence of stellar physics. As the Sun fuses hydrogen into helium in its core, the core gradually contracts, temperatures rise, and the rate of fusion increases. The Sun's luminosity has increased by approximately 30% since it formed 4.5 billion years ago, and it will continue increasing at a rate of roughly 1% every 100 million years. This brightening is imperceptibly slow on human timescales but relentless on geological ones. Over the next billion years, the Sun will deliver enough additional energy to Earth's atmosphere to begin pushing our planet toward the conditions that Venus crossed long ago. The inner edge of the habitable zone will creep outward. Earth's oceans will begin evaporating at accelerating rates. Water vapor will accumulate in the upper atmosphere, where solar ultraviolet radiation will dissociate it and hydrogen will escape to space, precisely the process that stripped Venus of its water billions of years ago. Earth will not remain habitable forever. The same star that makes our world possible is slowly, inexorably, turning it into the next Venus. The timeline is long, roughly 1 billion years, possibly somewhat more, before Earth's oceans are significantly compromised. 2 billion years perhaps before conditions become incompatible with complex surface life. These numbers dwarf every timescale in human experience. Civilizations rise and fall in millennia. Species evolve and go extinct in millions of years. 1 billion years is an abstraction, a number so large it resists emotional engagement. But the mechanism is not abstract. It is the same mechanism that destroyed Venus, the same greenhouse feedback, the same water vapor amplification, the same hydrogen escape, the same irreversible loss of an ocean. The only difference is timing. Venus reached the threshold early, possibly from the very beginning of its history, because it orbited 30% closer to the Sun. Earth has not reached it yet because our greater orbital distance brought us billions of additional years. But the clock is running. The Sun does not care about timelines. It brightens at the rate physics dictates, and it will continue brightening until it exhausts its hydrogen fuel and expands into a red giant roughly 5 billion years from now. Long before that expansion, Earth will have crossed the threshold that Venus crossed first. Our planet will lose its oceans, lose its carbon cycle, lose its atmosphere to solar wind stripping, and arrive at a state that, in its broad outline, will resemble the Venus we observe today. Earth's appointment with Venus's fate is not a possibility. It is an inevitability. The only question is when. There is something profoundly unsettling about a warning that you can see with your naked eye. If Venus were a distant exoplanet known only from transit data, its story would be intellectually interesting but emotionally remote. A data point in a catalogue, a cautionary tale discussed at conferences and published in journals and then filed away. But Venus is not remote. It is the bright point of light you see in the western sky after sunset. It is the planet your children point at and ask about. It is closer to Earth than any other planet in the solar system, close enough that at inferior conjunction it passes within roughly 40 million kilometers, close enough that the light you see from it tonight left its cloud tops only minutes ago. Venus is not a theoretical example of planetary failure. It is a physical one, hanging in the sky, radiating reflected sunlight from the same sulfuric acid clouds that seal in the heat that maintains the 465-degree surface below. The record that Venus carries is written in isotope ratios and atmospheric chemistry and radar-mapped volcanic terrain, and the crushed remains of every machine humanity has ever sent to its surface. It is a record of how a world nearly identical to ours, in size and composition and age, lost its water, lost its climate regulation, lost its magnetic protection, accumulated 92 bar of carbon dioxide in an atmosphere that now traps heat with a ruthless thermodynamic efficiency, and arrived at a stable state so hostile that the longest any human technology has survived there is 2 hours and 7 minutes. That record is not ambiguous. It is not open to multiple interpretations on its most fundamental point. Something went wrong on Venus. Something comprehensive. Something total. Something that turned a planet that could have been Earth into a planet where the surface glows faintly with its own thermal radiation in the near-infrared, visible to orbiting spacecraft as the waste heat of a world that has been cooking for billions of years with no prospect of cooling down. The missions we send in the coming decade, if they survive their funding battles and launch windows, will sharpen the details of this story enormously. Da Vinci will tell us whether Venus ever had oceans and when it lost them. Veritas will show us whether the surface preserves evidence of water erosion in its oldest terrains. Envision will map the subsurface and reveal whether Venus's geological history includes episodes of plate tectonics or water-related mineralization. Shukrayan will probe the atmosphere and solar-wind interactions from a new vantage point. The Venus Life Finder may test whether anything persists in the narrow, habitable band of the cloud layer. Each mission will add resolution to the portrait. Each data point will constrain the models that tell us how a twin became a nightmare. But the fundamental story is already clear. The most terrifying planet we know is not a gas giant with a radiation belt that would kill you in seconds. It is not an ice world in the outer solar system shrouded in methane haze. It is not a rogue planet drifting through interstellar space without a star to warm it. The most terrifying planet we know is a rocky world, almost exactly the size of Earth, made of almost exactly the same materials, formed at almost exactly the same time, orbiting almost exactly the same kind of star, sitting close enough to Earth that you can see it shining in the sky on any clear evening. It is terrifying because it looks like it should have been us. It has every structural credential to be a habitable world. It has the right size, the right mass, the right composition, the right position in the solar system. And yet it became the most hostile, solid surface ever measured. A world where the atmosphere is a weapon, the surface is an oven, the clouds are acid, and the geological record of whatever came before has been largely overwritten by planetary-scale volcanic resurfacing. Venus is not terrifying because it is extreme. Extreme is just a number. Venus is terrifying because it is plausible, because the difference between its fate and Earth's may have come down to a 30% difference in orbital distance and the chain of consequences that flowed from that single variable across 4.5 billion years of planetary evolution. Because the carbon that fills its atmosphere exists on Earth too, in almost the same quantity, held in check by liquid water and weathering and ocean chemistry and plate tectonics, systems that are powerful but not eternal. Because Venus demonstrates that a world can have everything it needs to be habitable and still end up as a planetary catastrophe if the conditions that maintain that habitability are disrupted. Because the sun that sustains us is the same sun that will eventually do to our world what it did to Venus long ago, on a timescale that physics has already set and that no human action can alter. The most terrifying planet we know is not hidden in deep space. It is not waiting to be discovered by a future telescope. It is not a theoretical construct or a hypothetical scenario. It is right there, 25 million miles away at closest approach, bright and beautiful and silent, carrying 4.5 billion years of planetary history that ended in the most complete environmental collapse ever documented on a rocky world. and carrying, in that same silence, a preview of how all rocky worlds eventually end when the star they orbit brightens past the point of no return. You can see it tonight. Step outside after sunset, look west, and find the brightest point of light above the horizon. That steady, luminous, unblinking glow is Venus. The twin that never was, the world that went wrong, the warning next door,